All right. Thanks for tuning in again. I know that last video was pretty long, and now we'll talk about the last topic: k nearest neighbors. This is an algorithm for classification. It is actually a very simple algorithm, and maybe we can get through it quite quickly here. Well, I shouldn't make any promises here. Um, so the idea with k nearest neighbors is that you are going to take a new test point, okay? And your training data is full of all of this data already, and you are going to measure the distance of your test point to every other point in the data. And so Euclidean distance is often used, okay? And this can be in high dimensional space, okay, not just two-dimensional. All of our examples would be two-dimensional, but it can exist in some high dimensional hyperspace or something, and you're still measuring Euclidean distance. So this side squared plus this side squared, it forms kind of your hypotenuse, and that's going to be your Euclidean distance. And you're going to measure it to every single other point in the training data. And so depending on how big your training data is, this can be very, very computationally expensive. So if you have like 1,000,000 observations in your training data, then measuring the distance, you have to measure 1,000,000 of these distances. You have to take your test case and measure it to every single point in your training data set, which can take a very long time. And so, for this reason, k nearest neighbors has fallen out of favor for large data sets. But it's simple and it's easy to explain, and it's still used quite a bit. But for large data sets, we generally don't even attempt to do k nearest neighbors. Okay, but anyway, once you've calculated the distance to every single other test case, you're then going to sort it. You're going to sort them from least to greatest. So you're going to find the nearest neighbors first, and then at the bottom of the list will be the farthest neighbors away. And you are going to pick the k closest ones. So k could be 1, and that's going to just use the 1 nearest neighbor. K could be 3, and you might use the 3 nearest neighbors, or k could be 7, and you use the 7 nearest neighbors. All of that goodness, and then so if you take k equals 7, you've got 7 nearest neighbors. You look at the class labels of those 7 observations, and then they each quote get a vote, and whichever class has the majority vote wins. So for example, if you take your 7 nearest neighbors and 5 of them are class A and 2 are class B, then you're going to label it class A. All right. For another test case, if you take your 7 nearest neighbors and 3 are class A and 4 are class B, you're going to label it class B. Okay. So how do you pick K? That's a tough question. You can use cross-validation. That's often our answer for a lot of these things. You say, well, let's try k equals 3, let's try k equals 5, k equals 10, or 7 or something. And you say, well, how often do I end up making mistakes using kind of this training data, validation data strategy, okay? And with cross-validation, you know the correct answers in your validation set, and you can see how often you are right or wrong. In general, k equals 1 is too small, and as k gets bigger, you end up, k equals 1 is too small, and you're going to make a lot of mistakes, and you're going to be overfitting the data. And as k gets really big, you'll be experiencing the opposite problem of underfitting the data. Okay. There's a situation where you get ties, and if there's only 2 classes, you can avoid this by just choosing an odd k, right? If k is 3, 5, 7, 9, some odd number, there's never going to be a tie if there's only 2 possible classes. Okay? But if k is even, you can end up with ties. And if you have more than 2 classes, you can have a tie. So even if you have k equals 5, if you have 3 classes, you can end up with 2a, 2b, and 1c, and you have a tie for a and tie for between a and b, having two votes each. And so, how do you resolve ties? There's not like one rule for everything. There's a few situations. One is you can just designate it as no class and just say, well, this is unclassified because there's a tie here. That's fine. You can use one nearest neighbor. You can just say, well, okay, I'm going to look at the, we're going to switch to nearest to neighbor mode, okay, the one nearest neighbor. There's never going to be a tie there. You can randomly select among the top tied groups. So if you have 2A and 2B, you can just flip a coin and say, all right, we're going to go with A, or we're going to go with B here. All right. Or you can say among the tied groups, select the one with the closest neighbor. That's not necessarily going to be the class of the one nearest neighbor. So you can imagine if you have k equals 5, 2 are A and 2 are B. It's possible that C is the one nearest neighbor. And so you might not want it to say C. You might want to say, well, let's look at A and B because they were tied for the most. And we're going to pick between A and B which one had the closest neighbor or something. Okay, these are scenarios to think about. In R, you're just going to use K and N, and they have a few things to deal with it. But let me just kind of show you a bunch of pictures for how this might look. So I've purposely generated some noisy data here, where we've got a little bit of overlap between red and blue classes, and we're going to just try out a test case and see how this is going to get, our test case is going to get classified. Okay. So here I'm going to put a test case right here at 0, -1, and we want to know, should this be classified as red or should it be classified as blue? And I purposely picked one that's a little bit ambiguous to see how the k nearest neighbor algorithm works. Okay, so first we're going to have to calculate the distance to every single other data point. Now when you have it graphed like this, you're like, well, why would I have to calculate distance? I really only have to look at like this neighborhood surrounding here. Okay, but when it's just straight data, okay, and if it's especially in high dimensions, it's really difficult to visualize distances in these high dimensional settings and also with just numbers. Okay, visually our brains are really good at estimating distances when it's in 2 dimensions, and we just go, okay, well, this one's the nearest, and it's going to be very close between these two right here. We can easily tell that visually, but the computer doesn't have kind of our optic sensors, and they just have this columns of values, right? You got x1 and an x2 column, and it just says, okay, here's a point at -1, -2, and here's a point at -1.1, -1.3, and here's a point at -1.7 and -2.1 or something, and it's just all of these values going down, and here's your test case. Which one's the closest? Okay, it's you end up having to calculate the distance to every single other data point because there's no other good way to calculate the distance and figure out which ones are the closest just by looking at them. Okay, a human, we can look at this and say, okay, these ones are the closest. The computer can't do that. Okay, and in high dimensional space, I don't think a human can do it either. Okay, in 2 dimensions, 3 dimensions, we can probably do it. Higher than that, I don't think, our brains can't even picture it. So anyway, we calculate the distances. We're going to get a matrix of all the distances. And we basically say, all right, let's pick the one nearest neighbor. So here I drew a circle around to kind of show that this is indeed the closest neighbor and nothing is closer than that. And in this case, with k equals 1, we're going to choose red. This test case will get classified as red because there's one observation, it's red, and so we're going to do that. Okay, with k equals 3, okay, these are the three nearest neighbors. This is the closest, third closest one, and so there's 3 here. 2 are red, 1 is blue, and so we're going to classify this point as red as well. Okay, 2 red, 1 blue. Okay, if I go up to k equals 5, I've got 3 blue. These are the 5 closest neighbors. I've drawn a circle around it. Okay, and we can see this one was almost there, but this one was indeed closer. So we got 3 that are blue and 2 that are red inside this circle. So this, with k equals 5, we're going to get, we're going to classify this as blue. And with k equals 7, okay, these are the 7 closest observations. This one is very close, and if I did k equals 8, we would have picked this one, but anyway, at k equals 7, we have 1, 2, 3, 4 that are blue, and 3 that are red. So we're also going to classify it as blue. All right. So that's how that works. Okay. Here's another test case. I'm going to put the observation test case at 1, 1. Okay, right here. And again, we calculate the distance to every single other data point. All right, and visually we can say, all right, well, this one's the closest, and then well, maybe this one and this one, or something like that. And so here, let's just see how it goes. Okay, so this one, seems a little bit more like in the red territory, so we're probably going to keep classifying as red, but let's just go ahead and take a look. So with k equals 1, we're going to classify this as red. With k equals 3, okay, we have 2 red and 1 blue, and it still gets classified as red. With k equals 5, okay, these are the 5 closest data points in our training data. We got 3 red and 2 blue, and so we're still going to choose red. And then with k equals 7, we got 1, 2, 3, 4 that are red, 3 that are blue, and so we're still going to choose red. So this test case is going to get classified as red for k equals 1, 3, 5, and 7. And you can keep going higher there. Okay, I did not include these. These are some slides that I prepared for a different class, but this is just kind of, I wanted to show you what KNN boundary regions look like for different values of k. This was done by, if you look closely, you can see kind of this tiny, huge, this grid of all of these points. And basically, it was kind of computationally expensive, but the computer, basically for every single little dot here, it said, okay, we're gonna use the k equals 1, and we're gonna classify, all right, so this dot is closer to this thing, the one nearest neighbor is this, and we're gonna classify this as blue, okay? And for this dot right here, the nearest neighbor is this point, and so it's gonna get classified as red, okay? And so this ends up being the boundary for k equals 1, and you can see it forms kind of this jagged thing. This boundary, on this side of the line, this is the closest one, so it gets red, and on this side of the line, this is the closest one, so it gets blue. Okay, and similarly, on this side of the line, this is the closest, and on this side of the line, this is the closest. So we're going to get that. So that's k equals 1. At k equals 3, this is interesting, okay? But what's happening is, for like this dot right here, or here, even like this one, for these dots, these are the 3 closest neighbors, but 2 are blue and 1 is red, so it's going to get classified as blue, okay? Over here, if you look at the 3 dots that are closest, okay, it's going to be this dot, and this dot, all right? And so 2 are red and 1 is blue. And when you come here, okay, the 3 dots that are closest is this dot, and this dot. So these dots get classified as blue, all right? And so basically every single dot, this whole grid got calculated, and they said, what are the 3 closest ones, and classified as red or blue, all right? And then here it is for k equals 5, and at k equals 7, okay? And so with the idea being, with k equals 1, you got kind of this all sorts of weird shapes, and as the K increases, the shape gets a little bit smoother isn't exactly the right word, but it becomes a little bit less flexible. Okay, it's kind of forming. It's like the line wants to become a little bit more simple. Okay, and I know it seems like there's a bunch of little jagged edges here, and that's always going to be kind of the case. Um, but you can see between here and here, there's definitely kind of more of these outlying things. Let me just show you what happens when you have a whole bunch of data. Okay, so here's a whole bunch of data, and we can see, this blue dot is kind of surrounded by red dots, and this red dot surrounded by blue dots, and what happens? Okay, with K equals 1, you get all of these weird enclaves and exclaves, okay? I don't know if that's the right word, but basically, in this zone, you ask what's the nearest neighbor right here, okay, to this dot, the blue dot's the closest thing, okay? And so everything in this zone gets classified as blue, okay? And when you get over here, yeah, the red dot's closer, all right? As far as in this zone, what's the closest one dot? You get this blue. And so you get these weird things going on, right? And you get this weird boundary showing up between the red and the blue, right? So again, if you look at this and you said, draw a boundary between red and blue, how would you do it? I don't know. Would you draw something? It's a little bit strange, right? So you kind of want to get some kind of boundary, and you're not quite sure how to do it. K equals 1 gets this really jagged boundary. It even draws these little envelopes around each of these things. As we do increase the K, you'll see the boundary get a little bit smoother. Okay, but smooth isn't exactly the right word. Okay, so here it is with K equals 3. Okay, you still get this weird enclave thing. Okay, like a point right here. These two blue dots are these 3 dots are the closest, and 2 are blue and 1's red, so it gets classified as blue. But compare this versus this, right? This looks a lot more smooth and reasonable. Okay, even though these 3 red dots get misclassified. Okay, and at K equals 5. So I'm just kind of scrolling through 1, 3, 5, okay, 1, 3, 5, and 7, okay. So 1 has all of these weird shapes. 3, 5, and 7, you get something a little bit smoother. Again, you still get a little bit of tiny jagged pieces, but overall, the shape of the boundary is indeed, I think, smoother, right? Or over here you got, so here's 1, here's 3, 5, 7, okay? And then I'm going to jump up to K equals 20, all right? And you get almost like a straight line boundary between the red side and the blue side, all right? So that's just kind of what happens as you increase the K from 1, 3, 5, 7, and 20, okay? And we get a little bit of, I think, something weird, because I think in some of these cases we're getting tied values. And so with K equals 20, you can end up getting ties. But here, just kind of illustrating what happens as you increase the K from 1 to some higher number, okay? And so, yeah, overall, does this seem like a good boundary between red and blue? Yeah, overall, but we're gonna get some points lost in the shuffle when you just kind of draw a straightish line between the red and blue regions there. And again, the drawback with K nearest neighbors is that you have to calculate the distance to every single other data point in the data set, which is undesirable. But it's simple algorithm, and can be useful. All right. Well, thank you for watching all 3 of these videos here, and I hope you guys are all safe and doing well. And we will see you guys next week. I will also, you can also look forward to the homework assignment being posted in the coming days. All right, thank you very much. Hope you have a good night and good day.